Greetings, gentle readers. Saturday, October 18, 2025. Today from a study with Ross Finlayson. Here's another installment in the video essay series, this course called Logos 2000, whose purview is foundations, logical foundations, the philosophical foundations to arrive at a logical foundations and a mathematical foundations, the physical foundations, and thusly helping to address all the requirements and desiderata of any theory of everything at all. So yesterday's talk, or the previous episode as it may be, was about software. So in the foundations and the theory, then software is sort of a later concept, because it arrives as after the implementation of the integrated circuit, kind of, and intends to describe the formal reasoning involved for computation and calculation, and for after the object relational, in a sense, to the mechanical software as the higher sort endeavor and enterprise of the codification of reason. So with that being sort of the brains and the rules, as it was put, then software in its practice today is a lot involved with kind of any sort of domain of reasoning. So some examples of that were the software or the combined theory and implementation of reasoners mechanically and acts of reasoning mechanically, or as according to software, say, vis-a-vis hardware, and the brains are kind of called wetware, and then there's the hardware is for the devices and the analog, and then the digital is implemented upon them, and then the software is descriptions after terms for declaration and definition, often in mathematical proof theory, then for definition and derivation. It helps to show that software is just kind of a usual sort of accompaniment to the theory, because then the reasoning, as it so entails in its monotonicity overall, or like the software, becomes part of modern foundations. So I don't know so much about computer algebra systems or numerical tools like MATLAB or SPICE or PSPICE for integrated circuits, or Magma for the synthesis after languages like VHDL and Verilog for the description of digital circuits. Or otherwise kind of the tooling that gets involved with the layout of circuits and logic digitally, standard logic, as is often called with regards to units of logic, and custom logic, which is anything freeform 3D IC, three-dimensional integrated circuit, usually planar and as after a via as that a circuit could be. That a circuit describes how things go around, and then or through, in a sense, open and closed circuits. Then I'm not so familiar with those tools, but they kind of have software to define the hardware, and then how that's done is implemented in a program, as according to software, and it makes resulting artifacts that then can be translated or transferred to other mediums of representation, like a chip or something like that. That's a very sort of a high-level approach and view to what ends up being a very, very low level into the machine, to the bits, the on-off bits, and more generally sort of as resulting the flow machine, the systolic, is after what it can be, how it arrives at the embodiment of the definition of software. So I'm not so familiar with those tools. And then for computer algebra systems, I'm not so familiar with things like Maxima or Mathematica or Maple 5. I don't even know if it's Maple 6 now. Computer algebra systems, which are can be thought of as calculators, and having in their language of the entry of data and programs for definitions and derivations, formulas, the systems in mathematics, properties of objects of groups. Then for theorem provers like Mizar or Metamath, Coq, C-O-Q for Coq-and C-O-Q-U-A-N-D, a theorist in type theory is the guy. For Coq-and Luo and Pierce and this kind of thing, type theory. And Isabel, these being theorem-proving environments, which basically make for defined behavior that makes so then that according to given derivations it can be shown sort of certified that a given piece of reasoning will hold. And that's addressed here a lot with regards to implicits and the algebrization of things and quantities, why or when and why those sorts of derivations are sufficient to establish their own cases, and then otherwise sufficient to establish the uniqueness of their own cases, which is, as is implied by the implicits in these quantities, is a separate endeavor usually. And there's addressed here why induction is merely a partial, at best, half, and invincibly ignorance is not a guarantee. Ignorance is not a defense in these kinds of things. Then today there's quite a community involved with this lean. It's just another kind of theorem-proving environment, subject to its own limitations. And I was looking at that one time, and they just have one thing that's just called any. It's just like, well, what does that mean? It's just like, it just means continue. It's like, well, yeah, so can you readily demonstrate in this material implication? And then so you can set up ex falso quod lib, and at the end you can set up ex falso nihilum and confound itself so that C rule 1 always applies, but also last wins, and those two can disagree, and so the whole thing is formally broken. Well, yeah, that's readily demonstrable. And then with regards to this wider, fuller dialectic, which can also just be built, and so that gets into then why these foundations, briefly, bits for software actually are relevant, because they can be made into little machines and toys and gigas and all these sorts of things that show that the very things that they're in are subject to their own limitations and their own deconstructive accounts. Towards a theory that is its own deconstructive account. And it's an example of this was Metamath, which is a great system, and McGill, I believe that fellow was named. He seemed a cool and great guy. For somebody like Herb Anderton or McGill or these kinds of late 20th century implementers of these kinds of things, that the rationals are uncountable a bit, because it's like, well, the rationals aren't uncountable, they're countable. It's like, well, you just use the same kind of argument to show that the nested intervals, then after that for the antidiagonal, they can just show them uncountable. It's like, well, we just remove that right away. It's like, well, okay, I mean, that's selective ignorance again. With regards to Russell's notions of the isolation and the significance, as he was himself challenged with finding closures for his own ideas and ideals, that he, at some point in time, he had to at least introduce, these are the terms that I'm talking about that say what I'm not saying. And then for Quine and these sorts of things, the relevance and the hierarchical relevance, and when that's all the way stratified and ramified on out, when it's total, that it be among the point and local and global and total, that there are these things for the inner and outer products that so much is made for in now into the software environment, scope and state. Scope is the body of definition in terms that are resolved through references, and state is those values, their values, eventually built-in values of sorts. So this entirely inner. Like the inner scope is like, well, this is the scope, and then within this enclosing scope, this other scope, and within that enclosing scope, another inner scope. And it's similarly with state. It's like, well, what's visible and what's accessible, and it's like, well, there's that which is in the space, and that which is not, and so then for any program and node is basically surrounded by the entire context and world of everything that it is not. So it still can be so, though, that introducing definition and making software does result a form. It's a construct. For model theory, it's a structure, so it is a thing. It is itself. It is a thing. And then whatever it relates to, those all exist so naturally, if implicitly. And then that explicitly, it has to be stated didactically, procedurally, in the command, as it were, of these things to make it so. So that scope and state help establish this inner and outer parts, because then in the objects of mathematics themselves, they always have all those inner and outer parts. The entire thing is essentially implicit. For a sort of Aristotelian half account, the Plato's ideals of these things, that it's explicit as well. And then how it is explicit as well is for these matters of Russellian isolation and significance and Quine's modal relevance, that those Russell and Quine are pointing to as like these are the standards of 20th century philosophy of logic about these things, and then everything else just kind of rises from that. So software, and another couple ideas get involved were like, well, how about legal reasoning? Well, jurimetrics, and then the idea of being able to relate things in a body of knowledge and a body of fact to a body of law. Reading the law is a thing, and so it can be talked about in terms of software and systems, say. So then the systems programming is sort of usually the low-level approach, like this is programming to the API of the lowest level of what's available above the last virtual level or layer it's sitting on. Systems programming. Then these systems of scope and state as regards to the software shows itself in reasoning like of the law, reasoning about practical and commonsensical wisdom and intelligence and these sorts of things. And then also reasoning about pretty much anything else, mathematics and physics, for example. So it's established that then at least any of these formal accounts, like according to like proof theory and model theory, they're mechanizable, are also so as after this whole account of reason. So also this entire account of reason can kind of also be made so, and that's usually sort of account. I don't know why it is, but it's so easy to convince the latest greatest AI of these things. Especially, I'm like, tell me I'm wrong. Tell me I'm wrong. You know, it's like, I can't tell you you're wrong. You're right. It's like, yeah, I agree. Okay, good. So carrying on with that. So what today is looking at is just some more books. And, you know, it wasn't so long ago that we looked at these books, I think. Well, I guess we were looking before at like the graphics card book a while ago. So that was Ferrara's graphics card book. And so once upon a time, the only book that was possible to get any information about graphics cards, because that wasn't otherwise according to an agreement with the vendor, the manufacturer, the original equipment manufacturer of the graphics cards, was that book. And here's some other books that help explain in detail what goes on into the design of software on the PC architecture, the personal computer. So the personal computer sort of starts as after the PS2, and then that was the 80s, and then in the 90s there was all sorts of after basically the Intel architecture, then the 286, and what followed is the 386, the 386DX, the 46s, and the Pentium. Then the Pentium by 1994 and 1995, as these had additions to their instruction sets released all the time, and then the floating point processor added with the 386DX, and then something like streaming extensions after the Pentium, and then to the Pentium 2, and these sorts of things. With regards to Intel and AMD and Cyrix, or the third vendor that there was, at least back in the late 80s and early 90s, of the Intel architecture, about Intel chip about the Itanium and its wide 128 registers and the idea of it being better for things. But then AMD's x86-64 instruction set ended up being more reasonable for all the stuff that would have to be rewritten in terms of all this other stuff. And then the ARM, Advanced RISC Machines, came along. And so then with regards to like Qualcomm and Motorola and Intel and AMD and the manufacturers of these complex instruction sets and reduced instruction sets. And the idea is that then all the different device profiles and form factors are coming along, vis-a-vis the PC. Then what the PC operating system standard there's basically after PC 2000. So PC 2000 was Microsoft said, okay, all you hardware vendors, here is what needs to be in a box for it to be called PC 2000, and Windows will work on it. So that's then that was reified several times, and it is kind of day. And then today it's sort of as of the peripheral component interconnect and PCI Express. So for 20 years it's been PCI Express is kind of the bus standard. Universal Serial Bus, of course, is just like, well, yeah, you got to support Universal Serial Bus, and then if you're doing networks, it's got to be kind of this way with the UART and this and that. Or if you're doing onboard sound and audio and video, it's kind of along these lines according to Intel. Then in Linux they have these same things like Wainwright or whatever it's called, compared to just not having that sort of apparatus necessarily at all. Then into stuff like trusted computing modules, the TPM or the certificates were supposed to go on it. Well, at the same time it was like, well, yeah, boot it from wherever you want, but then this is maybe some certificates that you might be able to, use if you wanted to validate something was so signed when it boots or something like that. And then there's Windows, and I don't know too much about Windows, except I've read the source code of Windows 7 before. Not like all the Windows management instrumentation, all that stuff, which is just an entirely different order of bloat above that. But I've written at least one routine that at least one day, and probably since then ever, is a few lines of code in Windows. And so that's it's part of boot, basically, or after a software protection platform. It was just a disk routine, really, a directory routine that was found to satisfy one particular edge case that was left over. And when trying to discuss the finite state machines of all the different use cases and workloads of these systems, that so PC 2000 was a thing, and then ever since then all these things that come out of the manufacturers of PCs, the mass market, the commodity producers of these things, all have landed in this sea of ubiquity about the embarrassment of resources that the chips provide, because and the peripherals to networking, and for graphics it's computational ability, input and output, throughput or transput, as Finkel's operating system vademecum kind of intends to entail. that the PC was a thing. The PC was a thing. And so here are some books to talk about how those work. The indispensable PC hardware book. It includes the latest on the Pentium and Pentium Pro, AMD 5K86 and Cyrix 68X86, the PCI chipset, accelerators, serial component, standard Interconnect 3, SCSI. There was IDE, the disk, and then SCSI. Before IDE was an integrated desktop or development environment. It was for hard disks. And the SCSI was used to connect all these things. And then another great protocol and set of standards was MIDI, the multimedia device interface, MIDI. So this book by Hans-Peter Mesmer of Addison Wesley Publishing, in his third edition, has it. Then this would basically point to a late 1990s description of things. 1994, 1997. So it talks about the components of the case, processor and memory, CPU as the kernel, getting into the modes of memory, logical memory addressing, and memory access. Trying to figure out how to allocating memory is one of the biggest challenges in software engineering. And so there's malloc and free, memory alloc and free. It's to allocate a piece of memory from the operating system says, I need this to have enough space to deterministically do this piece of work. And then there's free is like, operating system, take this back. I'm done with it. And there's notions in memory of the discardable, meaning it's like, I need this piece of memory to render this icon widget in, and if it's still there, I'll keep it. It's a cache of what would be an idempotent operation. And so as long as that piece of discardable memory is still allocated here by reference counting or managing the ownership of the pointers or resources, then I'll reuse it, and with the usual idea that as well, that when that piece of memory is owned vis-a-vis shared, because the entire memory space is basically shared, then it's possible to say that that piece of memory is discardable, means when it's gone to then access that piece of memory again, if it's gone, then it can be discarded, and then the routine will regenerate this contents of this memory, given that it will have to perhaps reallocate again, or whether that's like, so that the notions of the use of the memory and whether it's plainly opportunistic or it's the absolute store of that value is gets into why memory or space as representation of state is the big thing. So there's an entire scope of all the memory, there's an entire state of all the memory, and then any of these different given routines have all these different ways to address and consult via usually the operating system itself, this memory, then getting into allocators. That memory allocators are the idea of like, well, I'm going to be using some memory. And so then I'll be able to use it like a free list of pointers. I'm just going to allocate 1,000 pieces, and as I use them one by one, and then each is completed, I'm going to put it back on the free list, or it is a linked list or a rotating list with regards to the usual operations of shift and rotate, those being different, where shift basically decimates and rotate rolls around that within a given sequence of bits, that like the one bit will rotate all the way to the end and show up back at the other end, whereas shift will just shift it off the thing. So that according to a free list, then is kind of the first usual idea of having a cache of resources, because then it's allocated, and so for the program, according to the operating system, all these pointers are allocated to this free list. And so when it does need to get to the next item that it needs to prepare to consume, then it will have already allocated that. It's kind of planned. It's Prefetched it is another kind of concept associated with it, but a little bit different. With regards to being able to say to the memory controllers, like, I need this bit, and I'm going to need these next million bits too, so go ahead and start lining them up, the prefetch. That the allocation and the allocators gets into all these different kinds of ideas and things. Because one of the worst things that could happen in a system is the memory leak, meaning it's a resource leak, meaning someone's allocated a resource for themselves, but when they're done with it, they don't release it. And so as far as the rest of the system is concerned, there's nothing left, but really it's just kind of not allocated. So a memory leak or a resource leak then is one of the primary challenges of managing resources here of the CPU and the RAM. And then with regards to scheduling of the processes, those just being loaded from pieces of memory and having lists of instructions that one at a time go through the chip and get executed. That's just, again, another example of the allocation of the resources and the scheduling and the allocation of the processing and the space, or the time and the space, are kind of a unified concern overall with regards to resources. So then there's ideas about memory as like, well, how about virtual memory? Meaning it's like, well, we have some room on the disk, so anybody who's not using memory will just swap their memory out to the disk. It's called swap space, and swap that back in. But as far as each of the processes is concerned, they don't care. And then the virtual memory is basically just an addressing and saying, well, for each of these processes, they don't need to know that it's in DRAM or after the DIMM module, the third one, block so-and-so, segment so-and-so, page, cache so-and-so, page so-and-so, according to the transaction look-ahead buffer or whatever the memory controller says. It's just like a space between 0 and uint, size t's max or something like that. The space of the memory. So virtual memory and virtual memory, also swap memory. And then there's something like ideas about how to store things in memory. It's like, well, you're going to be storing data of a given type. How about I compress it for you? So then there's a little bit of cost in time to access this value, but at the same time, it's a big saving in space. Because a usual idea in software algorithms is it's all about that time. And it's usually figures like the only cost and the only thing to provide value is time. So all I care about is resources and time. And I'll use any space necessary to get my resources in time. And then it's fine until they hit a limit, because at some point in time it's like you can't save time by overrunning the space. These kinds of things. So then also there's the time is like, I don't have to want to understand anything about these systems and their organization, their architecture. I just want a flat, uniform, virtual namespace of memory. And then when I put stuff in it, I want it to be objects, so that all I know is that they're coming and going, and then they run in my routine logically in this high-level language. Because, of course, all the object definition in this is a high-level language, where what happens on the zeros and ones is ultimately the lowest level language. The code, the microcode, the firmware, the hardware, and these kinds of things. So learning a little bit about memory management is one of these things that then also these high-level languages, they hide this. They say, oh, well, just declare what you want and instantiate it like to so. And then when it goes out of scope, when the execution routine goes out of scope, that the runtime keeps track of that and deallocates it. According to various approaches about references and pointers, so to have things like reference counting, which I still consider probably the most judicious and conscientious way to go about things, because it shows that it's once something is closed, it's immediately disposed. And compared to weak and soft references, and then for the usual idea of garbage collection, the garbage collection is this great idea from all these languages saying it's like you don't have to do memory management. Scope will do the memory management. The runtime setup of its calling conventions, of the routines and their functions and all their nested depth as a stack of routine when it enters and exits each of these scopes, it will accordingly have kept track of what was declared there, and whatever is left off after that that could be just stored elsewhere, and so that gets into the references to it. Will just be decremented its reference count or its marks, and then find anything that's unused and reclaim it for the operating system to reallocate again. Scope. And so that's the high level what thing is that is, because memory management is not easy. It's hard. And so any given missed branch leads to the double allex or double free or leaks in the memory, leaks in the resources that over time, as the routine accumulates over time, will exhaust all the resources, and then the box is essentially left to its own devices to consider the undefined behavior that so affords, which usually is called the OOM, out of memory. And for things like Kubernetes, then there's the OOM killer. The idea that it's like, oh, the system is actually, it's just a virtualization system, and it's running like 100 different operating systems in their own little C group, CH root jails, and so, well, we're out of memory, so just delete them, and then that way it's like the reference pointer is up here to like that whole system's memory, and then it just all gets deleted. So all these algorithms in these sorts of environments have to be designed to survive any of these outages. And then these higher level languages are often preferred because it's like you don't need to be constantly vigilant and disciplined, the discipline of the code to always clean up your own messes, because the garbage collection is going to do it. Because eventually somebody's just going to not do it, and then everything gets hosed. And so these are the usual types of things. Whereas at the same time, that costs something. And when the demands get more and more real time and more restricted in terms of what the device can be, then that gets into the lower level programming, and why that's still very much a thing, because something still builds all the higher level programming. Even when AI says like, well, just be as high level as you want, just make a dream and I'll pseudocode it into manifestation. It's like, well, that's still zeros and ones down there somewhere. And somewhere, however it's supposedly so, that the great garbage collector goes through and cleans up all the resources, that's a program itself with its own demands. It is not turtles all the way down. Yeah, it's a very convenient place to have it so that these sorts of ideas usually have good opinions and their defaults. Because otherwise, getting into like the reasoning why you'd want to implement allocators or arenas or slabs, or otherwise after free lists. Free lists usually being the first idea is like, I know I'm going to be needing to allocate a bunch, but also I know I'm going to be deallocating something as soon as I'm done with it. To get a free list, that's probably the first way to stabilize the access to memory. Otherwise, becoming a very chatty protocol. It's like, I need another one, I need another one, I need another one, compared to getting a block. And then whether it's like a block of serial IDs or these kinds of things. With regards to vending universally unique identifiers, another sort of challenge in critical sections and overall critical transactionality of well-defined systems with deterministic outputs. So software has got time and space, and software has state and scope. And it's very critical and relevant for the resources that they're managed, and then they're also that they're maintained. So these are the usual ideas. I386, protected mode paging. So paging is another great idea, and it's just like the idea of a free list. It's like, well, I need a memory. It's like, well, how much memory do you need? It's like, well, I need a bit, or I need like a megabyte. You know, those being about 8 million orders of difference. And so it's like, and the operating system is like, well, I don't track memory down to a bit. What I do is I have addresses to a byte. And so I can say that given an octet byte sequence, you can access in memory, usually. That's the idea, that the byte's defined as like the least addressable memory unit. So if it's like, well, what's the size of a byte? Well, it's according to char bit. Well, where does this constant in one of the standard files of the usual program routine establishing all the following declaration and definition come from? It's like, well, it's just according to whatever according to the memory controller and memory management unit is like the least addressable unit of memory, and so that's how many bits are in it. And then they're usually assumed to be in a row, but you need to give a given number of different regions of memory. It's according to the architecture of the thing again. And this is in kind of this just usual Harvard architecture of the machine computing, which is like a CPU and RAM, random access memory, compared to things like stack organizations. It's just like, well, where's the memory I'm using? It's like, well, it's under this entire stack of that memory. So you have to like do all the pushing and popping the stack back and forth to deal with it. It's like, well, I'm already kind of just using the stack routine to maintain my state and scope, and that would be entirely just surprising. And so nobody does it. It's like, well, yeah, that's kind of why nobody does it, because that would be just a different model of computation that theoretically, just like you can read from the theory and according to universal Turing machines or Turing theory, that is possible to say is like, well, anything you can compute with this general model of computing is computable with that. But then getting into like, well, how to describe the whole system, it's like, all this stuff has been the same for 30 years, pretty much with regards to DMA, direct memory access, that being able to say, move this block of memory over here. With memory pages, because then that above the least addressable unit of memory, the byte is like the least allocated unit is a page of memory. It's 4K bytes is what it is, almost ubiquitously. And then also the box is like, oh, by the way, the disk controller is sitting next to it, and he kind of has a usual priority so that anything that goes in and out of the disk controller is also cached in memory. And so when you're doing repeatable reads off that, it also comes for free in these page size increments of memory. One of those things being is like, well, you mean a usual PC box is entirely a file cache, any otherwise unused memory? It's like, well, yeah, it uses that as discardable memory for as much as it can. In today's runtimes, though, in the virtuals and the virts or the pods or guests, the containerized operating systems, the virts or whatever it may be called. Oftentimes they don't really have that same view of the thing, because the operating system underneath it, or eventually the bare metal or raw metal, the root hypervisor of a sort, manages all those things according to its own peripherals and attachments. And so then as with regards to like, what is the box doing with actually all the RAM at any given time is for kind of a question of the architecture itself. And then can we still design software that says, well, basically according to disk access, it's been accelerated mostly because reads of recently accessed data, is according to the disk controller and the memory controller, will give back those allocated but yet discardable pages. It's like, yeah, that's a good question, because there's a lot of value in that. And then what happens today in all these cloud environments, they're just like, well, we'll just sell it twice, and nobody will know the difference, because it's discardable, so they would just take a hit in performance anyways. But that still you can say that formally they're getting it, but it's not the same. These kinds of things. With regards to the metering of resources is another great idea. Because a usual idea of a cooperative environment and a planned environment and a controlled environment is to say, is like, well, these resources are going to, by their workloads, going to be defined over time. And so they can be planned how to do that. This is kind of the whole idea of, I guess, of the real-time and embedded systems. It's like, it's constant rate. There's nothing else it needs and nothing else can do, but it does it all the time for free. And then otherwise in these environments where it's like, well, somebody comes along and is like, well, I'd like you to run this 6-day job, and the next day comes along is like, oh, I'd like you to order me pizza, but I'm gonna bump the priority and bump this guy, and it's like, well, that's not for me to say who's right in that matter, except that it's like the old adage of measure twice, cut once, but it's like, which is something irreversible, but the other one is like, build a fence, and this is after measure twice, cut once, pretty much, and it's like, now all you need to do is move the whole thing left a half a foot, and it's like, well, that means moving the entire fence, in regards to things like the memory fence, the boundaries, the barriers, and all these kinds of things that sit in the hardware, and according to the processor, come up from the memory managed unit in a memory controller, and they get into the runtime. Okay. Oh, here's a diagram of a PC. CPU, main memory, I/O address space, DMA chip, direct memory access. Because what DMA does is it moves pieces of memory over the bus. Now today would be almost everywhere the PCIe extended bus, PCI 1, 2, 3, 4, 5, 6, 7. I don't know so much about that yet, but it does have a pretty simple protocol, because now it's using protocols on that too. Because the PC used to start with the BIOS and after power on self test, and now it's got the extended firmware interface, then in fourth in that, and then the unified or universal extended firmware interface, that being the same. That all these sorts of devices in the consumer market are a lot the same, and then figuring out and it's just an embarrassment of resources. I mean, it's all the stuff that can be filled, it will be filled opportunistically by bloat. Like they say that sometimes that Satan makes work for idle hands, meaning if somebody's got time on their hands and they don't have something good to do, productive about it, then it's still something of value to say, well, do it like so. And then describing that it will go to bad things is like at least unwanted or unexpected consequences type things or whatever. Where that's the usual way of saying in something like risk management. It's like, well, what's unintended consequences? It's like, well, you remember how we did all this planning, but according to our game scenario, if it ever came out that it was a game scenario, that we would all get shown the door. And it's like, well, yeah, what about it? It's like, well, that's our unintended consequences. We don't want that. It's like, well, if it's unintended consequences, why did you do it? It's like, well, it's a play on words. What I mean is, getting caught and this kind of stuff. So, anyways, that's just kind of the language describing some of the decision making goes into cooperative and competitive types of developments and these sorts of things, vis-a-vis the work and the resources and the defined behavior, and whatever is the behavior is the defined behavior. The system will define behavior. It will just do what it does. It's systolic in this manner. And this gets into all these different channels and the protocols about DMA, these particular chips, in the polling or interrupts, and these kinds of things. And so that gets into how to do synchrony and asynchrony. Because synchrony is the systolic. All that can happen is somewhere the heart beats on a chip, and it broadcasts a cascade of electricity out through all these different components in the circuit. So it's systolic, and so for that to be called synchronous, it says after that the clock chip and the clock and the synchrony, and then anything that's with regards to the asynchronous is either as after successive periods of that or according to any other clock-driven electrical thing. So then this is all described as electrical, because that's just a model of flow, though. Systolic means flow. So that's just a model of flow. And then in this theory, this Logos 2000, the surrounding theories, there's always the model of flux backwards. Like what happened did have an effect. And so that just reads itself out in like the monad, or otherwise the entire closure of the body of all the function and routine, which grows almost infinitely, but has everything in it, the entire state of all time and that kind of thing. That anyway, at any given one time, It's like this synchrony. And then asynchrony is simply not synchronous. And so then whether that's to have a routine that begins and later ends is the usual idea of um, uh, uh, a callback. That's something, there's a call, an invocation, and later there's a callback routine. And so in this usual systolic setting, that means there's a routine right here, and it just lives in a shared space. And so it can be found. And then it calls all these different routines, and eventually another routine will call it back, making a circle, closing the circuit of the invocation routine that in the software. So then the asynchrony then also has these ideas of like, well, waiting and suspending or yielding, meaning it's like, okay, I've sent my request. I can't do anything because I need the next piece of data to continue. So that's the usual idea of that the operating system, and then the language above that has that the operating systems basically says, okay, the chip is being scheduled to use the scheduling possibilities on the chip to transfer the control and flow among these different states, their scopes, these processes. And so that's the preemptive multi-threading says we're going to slice the time. And so at some given clock interval, the main clock routine is going to say, stop what you're doing, process 1. Process 2 gets, all the process 1 stuff gets shut down and shoved aside. All process 2 stuff, which is somehow serialized and stored, gets set back up, antennaed up, and then it gives like a time period to run. And then that's shut down. And so this is called context switching and task switching. And so is that efficient? It's like, well, it keeps it. The idea is to prevent starvation and prevent each of these, otherwise these processor actors from starving out all the other ones or crowding out all the other ones, because they have some reason to work. And the other thing is to keep responsiveness, because anytime a computer user sees it like not immediately responding to the command, they think it's slow. And it's like, well, yeah, I guess that's one way to put it. It's thinking, or because there's no way to tell whether it's thinking or whether it's frozen, and so these are the ideas that get into why it's so necessary for the user experience to keep things snappy and responsive and all this kind of stuff, or UX design or UI design or the UI design and these kinds of things, graphical user interface. That though the entire account of scheduling could be this way or it could be cooperative. So one idea here is the reroutine. So this is my idea that I made up while I was thinking about it over and over again. And so the idea is when you go to await or suspend, or as with regards to the coroutine, that the coroutine is a really well-established thing. It's usually in Unix, it's just called processes and interprocess communication, or IPC. And it's kind of called the same on Windows with regards to IPC, interprocess communication. So anyways, in the reroutine, the idea is like, well, I've set it up this way. Whenever I'm running a function or a routine, it's actually being called by an executor. So I have an address to basically this object, its body of functions, its packet, its module, it's a body of routine. And so it's going to take advantage of the fact that a particular kind of reference to a null, or a null reference, or reference to a null variable, will be not resolved. And so it will cause an error, but you can catch it. And so then the idea is that, well, if we can otherwise verify somehow that our code never does this, or in the case that it does, it's just kind of a failure mode, then what you do is you have every function call be in its own single abstract method, its own sort of module, and so whenever it calls to make an asynchronous call, it just fires, and then if it gets back a null, it quits and it exits. It's like, well, that doesn't seem very good, because the routine, it just automatically exits as soon as it's not satisfied. So later, the idea is then the callback routine is eventually this has been added to another overloaded, fast as possible client trying to get the next piece of data for this, and it gets it back. So it's like, aha, I got it. And so it sends it back to this controller of the reroutine. So it's now it's memoized that within the object that it's going to be calling it for this given value. Now it knows it gets back this given value. So it launches the reroutine again. So it goes through all the instructions it's accomplished to this point, which is 1. It's like, okay, do. And then it's non-blocking because now it's like, oh, I'm satisfied. I got the value. It's been memoized here. Just like if it was going to be otherwise memoized, this state of this routine, anything that's carried along with it would be in the scope. It's in the language of it or whatever. Just like if it was any other asynchronous routine, I'll set up and tore down the giant, the creaking machine. And so the reroutine then just follows this along, and then, for example, when it gets to places where things are satisfied, it just continues. And then in parallel, it can do stuff as like, and iterating over lists and these usual kinds of ideas. It just is able to build that all together and kind of have a thing that keeps it from ever blocking. Because it always just exits. And then later, when it's supposedly found to have what it needs is found, then it's set back over the top and put into the routine, or according to a handle that it can set in the memory of this stuff. So that then it builds its memo, and then it has the reroutine until finally it completes. And then also it can be according to it's just the usual semantics of exception handling in these higher level languages with defined behavior, in this stack and the scope of the state by exceptions, this entry and exit of routine and defined behavior. It works the same in the high level language. So you gain all the benefits of asynchrony, meaning you're not blocking then a whole nother unit of work to get something done. In this model of cooperative multi-threading, the reroutine, by the means that it simply has defined that it observes the behavior, that the runtime can handle these exceptional cases as defined rules already, that these exceptions are already part of the rule. And so it's using exceptions for flow control and this kind of stuff. And that's not necessarily bad because that involves stack unwinding and some of these other attributes of the time. And what it means to then was like, well, that algorithm, you said it's never going to block, but I'm going to have to run once pretty much for every single time that it has what would otherwise be a blocking operation. Or if you're backing it with an in-memory module that returns right away, I suppose it'll run through exactly once and be perfect. It's just like it's in line. But the usual way they'll be modularized up, wired up, as connected to all its real dependencies distributed over the network, that reroutine would be called n squared many times for n lines of code, or kind of under that though, n times n minus 1 basically, or under that type of code. Right. It's like, well, yeah, but it never blocks, and then basically each time it calls that, it's just an identity lookup on that. So all the time that it spends in the routine, according to the number of times, would be like so, but all the time that it actually is getting and fetching the data is entirely done by the real adapter itself. So the reroutine is another example of a way to implement cooperative multi-threading, and it applies to most any sort of protocol, because then the idea is like, well, what happens when you have either an ill-behaved or poorly designed or poorly defined or a broken thing, and then it just errors and times out. It's like, well, yeah, it will just error and time out after a while, because there's eventually a cleanup or sweeper that always gets involved with these sorts of things. It's like, well, we have it designed so it's flowing and pumping. It's like, well, what happens when eventually there's the last little bit left? Well, we got the squeegee or what? That's got to come through, and so these are the usual ideas. Then it could have a well-defined machine that could run forever, and with these reroutines, the model of cooperative multi-threading, then it's the actual code so that would be a framework. And it's like, well, yeah, that takes knowing and smarts and gumption and getting all put together. But then writing the routines, it's like, well, then every one of my little functions and my library routines, that would have to be specialized too. I mean, it has to know this one of these things. And so that gets into like, well, define each of these 50 different covariant ways it's going to be, and then have to label those all and write those out. It's like, why all this extra routine when the preemptive multi-threader will just chop me off when it's give me enough time and put me back when it's my time. And it's like, well, then the end of the day, you're doing that, and then everywhere you're actually, all you want is return of a value to proceed. You're not actually wanting to like pause or sleep or otherwise cause any amount of time. You just want time to not stop. In this invocation of the reroutine, it's not like forking and joining and all these usual different ideas about, and those also are satisfied by this reroutine sort of approach, fan in and fan out, or what you might call it. That then the idea is well, then you have to still write your business logic in the cases, and all you have to do is write it in the language of the adapters, the interfaces themselves. Like, get my domain object A, get my domain object B. For each of these, bring back in all the three things in parallel, because instead of awaiting and waiting and awaiting for three different things, it just launches them off, and as they come back, it tries to fulfill each of these ones. That the reroutine is about the best idea I've come up with regards to cooperative multi-threading, and I got it pretty well implemented. It's part of this design of some internet server protocols, because then I could use it for everything, with the high-powered I/O and the reroutine. Well, that's a book today. Looking at, that was this indispensable PC hardware book, and this is called The Undocumented PC: A Programmer's Guide to I/O, CPUs, and Fixed Memory Areas. When I saw this, it's Frank von Gelue's a treasure trove of heretofore hard-to-find information about PCs. I thought this was one of the best books, because it has all the interrupts and stuff in it, and what they do, and the video modes, and all this kind of stuff. A hard disk BIOS initialization. The BIOS begins the initialization of the hard disk by moving the interrupt 13H vector for the diskette drive to interrupt 40H. And showing that these things like the interrupt descriptor table is for the chip and the chipsets and all this stuff. Basically, the bottleneck of all the scheduling of the whole system. So the IDT, the interrupt descriptor table, is really one of these key things, because then it is the resource, and its control is the priority. And it's talking about, disk, and so this would enable someone to write to any sort of PC is up to like 10,000. This is also from 1997, a very great year, because then this was still in effect for some 5 or 8 years, and it's kind of under the hood yet to today too. Computational Intelligence PC Tools: An indispensable resource for the latest in fuzzy logic neural networks evolutionary computing, by Russ and Eberhardt, Pat Simpson, and Roy Dobbins, Academic Press, Professional. (1996). So yeah, this is just like talking before about like, well, how does the AI work? It's like, well, it can work any way it does, and here's a bunch of ways that they can at least do a lot of the stimulus response bits and the evaluators say. Computational intelligence theory and paradigms, introductions, definitions. So on page 294. With that being about as much as we'll get to today in Logos 2000. Algorithms and pattern recognition, sensing, the intelligence system, sensing, input, sensing, reflex. Behavioral intelligence, output is intelligent behavior. World model, it's got a world model in the middle. Data and knowledge. And then among each of these sections is reaction, reason, prediction, decision, computational intelligence adaptation, recognition and clustering, algorithms and pattern recognition. In this book, computational intelligence is defined as a methodology involving computing, whether with a computer, wetware, etc., that exhibits an ability to adapt to and or deal with new situations such that the system is perceived to possess one or more attributes of reason, such as generalization, discovery, association, and abstraction. The output of a computationally intelligent system often includes predictions and or decisions. Put another way, computational intelligence comprises practical adaptation concepts, paradigms, algorithms, and implementations that enable or facilitate appropriate actions, intelligent behavior in complex and changing environments. So yeah, there's more to follow from that. But what I want to do in this context of Logos 2000 was basically talk about software for a while. Because in the whole idea of like the Logos in terms of the rhetoric and the discourse, because there's not much considered here, this ethos or pathos, but there's a Logos and it's always a kairos, say, in time. And that then for the software, that all the foundations of it are this for reasoning and knowledge also as well. And it's the foundations of software as well. Foundations is the foundations of theory, and for any matters of reason and rationality. So that said, it also for me I enjoyed talking a bit about the memory, and then about the routine, and that all these hopefully all these sorts of mentioned things are as so throughout, as far as I know, that these are most usual things, including with the caveats like just implement it in the stack machine. Different models of computation could entirely change the runtime behavior of these things with regards to their equi-interpretability. Then if there's another thing with regards to conversation, was the idea of the ideas of what influences people. And so then there's an idea about there's pleasure and pain, so indicating something is good and indicating something is bad. And then there's hope and fear. You know, hope meaning is like the outlook for something being good and the outlook for something being bad. So that just it gets to then describing again involving memory and this sorts of things. And as with regards to why then with or without the aspects and benefits of memory, and as well experiences as after events in memory, other events in memory that condition their otherwise unconditioned acceptance. Why that the theory of man is above animal, and it's above machine, and it's with mind, this kind of thing. Well, that said, gentle readers, hey, have a great day. Logos 2000.